Hello, everyone. Okay, there are several Mathematica and ZMAX files posted for today on Blackboard. You might want to download some of those while we wait. I'm going to get rid of one of them because I realized you don't need the one that's, ironically, you don't need the one that's labeled working, because it is working, but I later realized it was a case that I didn't really want to discuss. So we'll wait a few more minutes. Only got 5 students so far. By the way, today is this coming weekend is one of the worst weekends of the year. Absolutely terrible weekend.
Why is that?
Well, we all have, they set the clocks forward. The best weekend of the year is in November when they set the clocks back and you get to sleep an extra hour. But this is a terrible, terrible weekend. And how many people do we have at this point? Still just 5 students. Where is everyone this week? I know that on Tuesday they had the excuse of a E&M midterm on Wednesday, but what's going on today?
I'm assuming mechanics midterm, I think.
Oh, there's a mechanics midterm tomorrow?
No, it's on Monday.
Oh.
So yeah, I'm not sure where they are.
Well, why would they start studying before Sunday night? Joking, we're joking. But anyway, try to get 1 or 2 more people.
I can vouch for Juan who's having internet problems.
Okay.
That's about all.
Yeah, but there's a lot fewer people. Only like half the class did the latest ZMAX assignment.
Wait, half? Wow. Isn't there like supposed to be 30 students in this class?
There's like 22 people enrolled right now, I think. My grading was easy. I mean, look, when people go, I only work as hard as you guys do. That's one of the things about, I work harder, but one of the things is that I only answer as many questions as you ask. I only grade as many things as you submit. So, the lazier you are, the better my day is. But anyway. All right. I'll wait 1 more minute. By the way, next week, okay, 2 things. First, I think I already mentioned this on Blackboard, but tomorrow there's a alumni panel at 3 o'clock, another one. This one was organized by the college. So it's going to be a different group, mostly people who are a little bit further along in their careers, which is good. I mean, it's different from what we had, and I think it's good to hear from some people further along. So 3 p.m. Friday, alumni panel. Here's the Zoom link.
Is it gonna be photonics people as well, or is it just all branches?
It's going to be a much wider range of people. Let me look in my email and see who was going to be there. Trying to find the description. Okay, Mark Helminger is at JPL. And then Vincent Kong is a senior manager at the Aerospace Corporation, which is basically a defense contractor in El Segundo. We have a few alumni besides him working there. It's actually a very nice place to work, and they're pretty good about things like tuition benefits. And Renee Jordan, I don't know anything about, but he or she, it's not clear from the spelling. Renee, he or she works at KLA Tencor, which is a company that makes stuff for the semiconductor industry. And a lot of that stuff involves optics, involves plenty of other things too. It's an industry that hires quite a few physicists. Aerospace companies and defense contractors hire plenty of physicists. You might think, oh, wouldn't they all hire just aerospace engineers? But the Aerospace Corporation is responsible for things like atomic clocks. And atomic clocks are really, really, really important for GPS. They're really, really important. I learned a few years ago for banking, actually, because they need to be able to timestamp transactions. I don't claim to understand finance well enough, but apparently if transactions aren't time-stamped accurately, then people could play games with when did this order or message arrive first, who did what first, and it would open up opportunities for mischief. Interestingly, I read a book called Einstein's Clocks, Poincaré's. I'm blanking on what Poincaré's things were, but Einstein's clocks, Poincaré's maps, I think it was. Yeah, okay. So Einstein and Poincaré both made big contributions to the theory of relativity. And both of them at some point did other things in their work, and both of them did things that are on the surface much more obviously practical. Einstein, working in the patent office, one thing he spent a lot of time on was clocks. And I don't necessarily mean those old 19th century grandfather clocks. I mean sensitive timing mechanisms. Telegraphs and trains required standardization of time because, again, if you're doing commercial things, if you're taking and receiving orders, and there are legal consequences attached to whether a given order or payment or whatever was received before or after another course of action was taken, you need accurate time stamping. Well, before we had modern digital technology and long distance communication, who cared? You see when the sun's going down in your city, and that's when night starts. You see when the sun is overhead, and that's noon. And if someone 100 miles away has the sun overhead at a slightly different time of day, who cares? It's not like you're going to get a message to them instantly. But if you can get a message to them instantly, and purchases and payments and order cancellations and all sorts of things with legal consequences attached to them are arriving constantly, then you need to figure out then priority and time stamping matter. If you have trains arriving and you say, well, this train is going to leave here at 1 p.m. and it's going to get to the next station at 1:25, well, 1:25 by whose time? And so Einstein apparently he spent a lot of time reviewing patent applications related to high precision timing. And Poincaré did a bunch of things with mapping because the French had a colonial empire. And so accurate mapping and navigation. And both of them in their work spent a lot of time thinking very, very carefully about what it means to measure the interval in space or time between two things. Now, I can't say, hey, that means that when Einstein worked on this whatever patent for whatever timing mechanism, that's where the idea for relativity came from. But in general, if you think very carefully about something in one context, sometimes it kind of limbers up your mind to think about it very carefully in another context. And I think we can say that about them. And anyway, that's why atomic clocks are so important. And the military cares a lot about atomic clocks for GPS, for communication, for navigation, for synchronizing of operations, for missile guidance, for tracking things. You know, if your task is to deliver a missile, to launch a missile and have it hit its target at a very precise place and time, all of this matters. And so atomic clocks are maintained by the military, but they're also of great industrial importance. And atomic clocks are based on electronic transitions, absorption or emission of photons in very high quality cavities. Just places where electromagnetic waves are trapped. So that's something that the Aerospace Corporation is involved in. And now we're up to 8 students. So I think I'll stop the history lesson and start talking about zoom lenses. Remember last time we were talking about the idea of a lens whose magnification or focal length could change. What I'm going to talk about today are called optically compensated zoom lenses. Last time, I talked about afocal zoom lenses. Did something with an afocal system. Got the spacing between lenses 1 and 2, and the spacing between lenses 2 and 3. And we worked out some formula that D12 equals some function of D23. And for a given value of D12 and a given value of D23, for the right pair of values, we could get whatever magnification we were hoping for. But that requires, it's a nonlinear relationship. It's a tricky thing to rig up mechanically. And so now what we're going to talk about is a much simpler idea. Oops. Optic axis, a lens. We're going to first do a symmetric relay, and we will do a symmetric relay with objects at finite conjugates. Right? So we've got 2 lenses here, then we've got some lens in the middle. The idea is that these 2 lenses are linked. They're mechanically linked. This one is fixed. These 2 are linked. So if this one moves to the right a distance x, this one also moves to the right a distance x. So the spacing is D23, oh wait, not D23. I'm going to call this D minus X, sorry, D plus, no, D minus X. This is D plus Why are fingers not connected to brain today? D plus X. All right. So if I move this to the right, then I get something here. And I get something here. So the spacing increases to D plus X. And of course, this spacing decreases to D minus X. And if the image forms here, this is S, this will be S minus X. And we'll initially consider a one-to-one relay. So this would be S, and this would be S plus X. Any questions on the setup and the notation? The idea is that this should be a fixed image plane. Now, it's not going to be a perfectly fixed image plane. It turns out that if we move the lenses a little bit, then the image plane will move slightly, but it doesn't move a lot. So in some cases, the image plane will be I'll draw it with a solid line. In some cases, the image plane will be here. In some cases, the image plane will be there. In some cases, the image plane will be there or there. But the idea is that these are all very close together. Right? So if they're all very close together, the image plane moves ever so slightly. It's slightly out of focus. But the spacing between the last lens to the image plane is S minus X plus just a tiny change, delta S. And you could say, well, shouldn't we then be moving the detector? And the answer is, I don't know. What does should mean? If should means in order to get the absolute best possible, well, then yes, of course, you should move the detector. Then we have a thing with more moving parts. But if you're trying to make something simple that has fewer moving parts, then you don't move the detector. You just accept that, okay, it's ever so slightly out of focus. And we'll figure out in a little while whether the amount that it's out of focus is a problem. Any questions so far? So we set up these matrices. First, we translate, call the translation matrix T, T of S plus X. Then we propagate it through our first lens, which I'm going to call, well, let's see here. I'm going to call this F minus F over 2 and F. So I'm going to send it through a lens, which I'll just call L of F. Then I'm going to translate it through S minus X. And then I'm going to send it through another lens. Then I'm going to translate it through S plus X. And then I'm going to send it through a lens. Sorry, that should not have been an S. That should be a D. These spacings are not all the same, my bad. D minus X, D plus X, a lens of focal length F, and then a translation of S minus X. Any questions so far?
Quick question, actually.
Yeah.
for like this was the same as the homework problem. For setting up your matrix operations here, I noticed that you kind of like set it up from left to right, starting with the leftmost lens. And that's how you wrote out your matrices.
Oh, shoot.
Okay.
Shoot.
That's what I was wondering. Is it supposed to be the other way?
My God, yes. Okay, well, here's the good news. The good news is that there's enough symmetry in this that I can just replace pluses and minuses. So this becomes T of S minus X. That will be the last step. S plus X will be the first step. Then we hit a lens of focal length F. Then we go D plus, no, that should be D minus X. Then we go through the center lens. Then we go through D plus X. And then finally S minus X. Thank you. Other questions? All right, so we can set up these matrices, but it's one thing to just say, hey, we've got all these matrices and this is what it looks like, but how do we know that's actually going to perform the way that we want? Well, what we would start with is pick S in terms of D, because we're going to get a matrix A, B, C, D. If we've got both of these at finite conjugates, so I've got an object at height y1 here. Now we're going to get an image at height y2 down there. We're going to pick S in terms of D. Then y2 is going to be C theta 1 plus D y1. So what do we need to do? What matrix element do we need to do something to? What's our condition to have imaging?
I C could be 0. So if we let C equal 0, it'll be the equation for magnification.
Yep, so let's pick S so that C equals 0. Okay, and we'll do all of this in Mathematica in a few minutes, but I want to sketch out the idea right now. So we're going to get some formula for S. So we're going to get S as a function of D. Now, what we want is ideally, the problem is if we play with S, that would be moving the object as well. Okay, so what we want to do here is pick S in terms of D when X equals 0. So we set up a much simpler case. We set up the case of everything symmetric. And then I drew this to scale. So 1. Get the simple case working. All right. Everything's symmetric. Nothing's been displaced yet. Okay. Then 2, when we start moving things, We're gonna like move the lens over to here. We're gonna move this lens over to here. And we're gonna move this thing, that thing, sorry, doesn't move at all. Right, the key thing is that this distance is s plus x. And the actual distance to our focal plane is s minus x plus some unknown delta s. This is d minus x. This is d plus x. D plus x. All right, we want to see shift two lenses by x. See if delta x, sorry, delta s is small some range of x. So I'll give you a couple examples. If this is delta s and this is delta x, if delta s looks like this would be ideal. Well, actually, ideal would be perfectly flat, but that's impossible. So this would be the next best thing. This would be great. You know, that would mean that any x value between like here and there, it barely moves at all, right? I would love to have that case. On the other hand, what if it's like that? That would be terrible, okay? And it turns out that depending on the value of D that you pick, depending on how far apart you put the lenses, which in turn determines where the image, the object and image should be, if you pick the right separation of lenses, you can get the blue case. If you pick the wrong separation of lenses, you can get the red case. Any questions on that?
So can Zmax do that for us by optimizing the thicknesses?
I'm sure it could. We would have to figure out, though, how to get Zmax to sample a very wide range of configurations. So I do that in Mathematica with the matrix calculations. So let's switch to Mathematica. Let's look at the Mathematica files that I posted. Under today's files, the one you're going to want is matrices zoom lens V7B. So give everybody a moment to download those. And I will tell you that of all the things I've tried to prepare for this class, zoom lenses are by far the most difficult thing that I've ever had to work on, because they're even harder than microscope objectives. Microscope objectives are one of those things where you know it's got a dozen different components. You know that those dozen different components are a trade-off between a dozen different considerations. You know it's complicated. And you know that there's a very simple principle in play. The deflection at each surface should be very, very small, okay? And you know it's weird, you know it's complicated, but you know why it's complicated and you just accept it. Zoom lenses are one of those things where every single explanation of it I've ever read seems so logical, seems so elegant, and then you try to do it and you realize that if you make even one tiny mistake, this whole thing just goes to hell when there's no obvious reason why it should go to hell. So does anybody need more time to load up that Mathematica file? Okay, so first, as always, we run those two commands to define our two basic operations, translation and a thin lens. Then we've got the definition of a triplet. All right. We're going to make things simple. We're going to say that F1, the first focal length, is just 1. Then F2 is chosen, F3 is chosen to be F1 so that everything's symmetric, and F2 is chosen to satisfy the Petzval condition because it's convenient. We hit Shift Enter, we run it, and we find that our 4 matrix elements are ugly things that involve S and D. So we got a 2 variable problem. But it's not as bad as you think, because even though there are 2 variables in this problem, one of them is determined by the other. If we set the spacing between the lenses, then we can figure out where the object and image should be. If we set the object and image positions, we can figure out what the spacing between the lenses should be. So we tell the program, hey, solve this equation. The lower left matrix element is equal to 0. Solve for S. So it does that. It gives us 2 solutions. And you can experiment with both of them. Here we're going to experiment with the second one. Right? So now we know if everything was nicely symmetric, we know where the object and image would be. But then we move things. Okay, the object position, the object distance becomes S plus X. The first spacing becomes D minus X. The second becomes D plus X. And the image position becomes S minus X plus delta. So now we set up a new matrix. And that new matrix no longer has S in it, but it's got this D that we can play with. It's got this X, and God help us, it has this delta. And it all looks messy. But we tell it, okay, solve the equation. We want that lower left matrix element to be 0. So tell us what delta will be. And it gives us a god-awful, ugly formula for delta. All right, well, delta S, I'm going to call it. We can work with that. So we tell Mathematica, hey, that's what delta S is. And fine, we create a function called delta S. It's a function of X and it's a function of D. And then we plug it into Mathematica. We say, let's plot delta S. And this manipulate means, let me play with D. So let me show you how that works. You just hit Shift Enter on this cell. And then we can play with D. And we see that if we choose the wrong lens spacing, whoa, that becomes huge. If we choose the right lens spacing, well, I can make it quite small there. Now, if I, again, choose the wrong lens spacing, it becomes quite big, but there's this sweet spot, and we want to hit the sweet spot somewhere around there. So we look at that sweet spot. It's about 0.6615. And I'm just going to code in, this is the default value. This manipulate command means that you're manipulating a plot. You've got this thing that you can manipulate, the slider bar that you can manipulate. And as you manipulate it, it changes the plot. And the thing that you're manipulating, the slider bar changes the value of D. D could be between 0.5 and 0.8. And the default is 0.6615. Any questions? I only asked you to skim the paper and the book section that I gave you because they use very different notation, but you should have at least seen some graphs indicating that they're basically trying to figure out when will an image shift be small. Well, this is kind of like one of those graphs. Any questions at all?
I have one, Professor. When you
Sure.
were moving the, changing the D value and looking at the graph, what were you trying to make it look like to say that it was the exact thing that you wanted?
I want it to be flat. You see, I want it to be for like this, for value around here, delta S, the image shift, is very small for a wide range of X values. For X anywhere between minus 0.2 and plus 0.2, delta S is almost zero. It can't be exactly zero, but it's very close to zero. All right, so I've got this wide range of X values where I can move my lenses back and forth by 0.2 focal lengths, and the image position barely changes. That's what the flatness of the graph. Now, it's not perfectly flat. We could zoom in on it. I'm going to have it plot this between, I'm going to kind of zoom in a little bit. And I'm going to have it change that to 0.05. All right. I'm going to, you see, if I play with this, right now, for almost any value of X, it's a negative number, and that negative number gets large very quickly. Now it's for almost any value of X, positive number, and it gets large very quickly. But for this particular lens spacing, you see how the image shift is almost zero? That's what we want. We want to know that we could change X, move those two lenses back and forth by 0.2 focal lengths, and the image barely moves. That's what it's telling us. 0.6655 maybe. Something around there. Other questions? All right, well, we're not done yet, okay? We know what lens spacing we want. We want about 0.6655. But there are some other things that we need to know. So we set up this matrix again. We ask, all right, we've got our triplet with these focal lengths, D minus X, D plus X. One thing we want to know is what is that lower left matrix element? Because I was saying that the lower left matrix element should be zero, but it won't be exactly zero. I want to know how much it deviates from zero, because Y2 will be equal to the lower right matrix element times Y1, but also be equal to the lower left matrix element times, times theta 1. And we'll get to the range of theta values in a moment. So we ask it to just tell us what that lower left matrix element is, and it tells us for different X values. By the way, here, I had it say that the image distance is not S minus X plus delta, but just S minus X. Because now I'm saying, what if we didn't go to that other plane? You know, what if we didn't move an additional distance delta X? Well, if we say, look, maybe the actual image is a little bit further off by a distance delta S. I said delta X earlier, I'm sorry. Maybe the image is a little bit further off by a distance delta S, but we're not moving our detector. We're keeping our detector right here, the first position we worked out. And yeah, that means that that the lower right matrix element won't quite be zero. We won't quite be in the focal plane, but we want to at least know, well, fine, if we're not quite there, how close are we? And the way we do that is we see, well, what is the value of that lower left matrix element? I'm calling it Q because it stands for quality. It's going to tell us something about the image quality. And we see that for a very wide range of X values, I'm going to go like minus 0.3 to 0.3, and I'm going to have it plotted from 0.05 to 0.05. For a wide range of X values, somewhere around there, somewhere around 0.6, and the lens spacing is like 0.66 focal lengths, give or take. We can debate whether it should be 0.6655 or 0.6555, but for something in that ballpark, we have that Y2 is not quite independent of theta 1. Y2 has a term that involves theta 1. It's this, but it's close. But it's a very tiny term involving theta 1. Let me explain what I mean. I'm going to go back to drawing. So again, we've got our optic axis, lens, lens, all right, object. I'm going to draw the object less exaggerated because everything's paraxial, right? So Y1. All right, and then Y2. Okay. Y2 is equal to C theta 1 plus D Y1. Now this D is our magnification, and this C is what I'm calling Q, the quality. So theta 1, ideally C would be 0, Q would be 0. But in fact, theta 1 is between the lens diameter, between plus or minus diameter over 2 S1. So that diameter is going to be, we'll just work with that for now. So Y2 will be magnification times Y1 plus or minus. You know, say, is it always either plus or minus? I just mean that it's within the range plus or minus Q times diameter over 2 S1. All right. But let's also note that the lens diameter should be small. Let me look in here. If we have, for simplicity, equal magnification, 1-to-1 magnification, then S1 must equal S2, right? And they must be 2F. Any questions on that assertion?
Wait, why do they have to be equal again?
Well, we're starting with the symmetric case.
Okay, that makes sense.
Yeah. So then we've got our magnification times Y1 plus or minus Q times the diameter over 4 F, because we got 2 there, and we got another 2 there. Magnification times y1 plus, I feel like I'm missing, no, I'm not missing anything. Plus Q, well, let's see here. Our F number is a common figure of merit for a lens, and that's F over the diameter. So the diameter over F would be equal to 1 over the F number. So we're going to Q times Q divided by 4 times the F number. And for most lenses, the F number is already bigger than 1. So it's very, very, very rare that you see a lens with F1. All right. So we're usually talking F maybe like 10. So we're probably talking magnification times y1 plus Q over 40. That's good, because if we go, any questions on how I did that? Why I did that? What I'm trying to do is I'm trying to figure out how much the object gets smeared out, or how much the image gets smeared out, excuse me. Because we know that if we move the lenses back and forth, that lower left matrix element won't quite be 0. We're going to have something non-zero. So y2 will be, this is what we want, plus this other term. But this other term will be like Q over 40. And that's good, because Q is usually small in the cases that we've been looking at. If you look at our mathematical plot, Q is like, it's less than 0.01 when we do it right. Yeah, it's less than 0.001 if we do it right. And let's look at a narrower range of D value, of lens spacings. So we get a little more. You don't want to bring it down too far, but the thing is, like, maybe there, I don't know. I go back and forth a lot. I feel like if I bring it down here, I am making my Q, well, it's negative. I'm making the magnitude of Q a little bit larger here, but it's still a minuscule number. And I'm bringing the range of useful values. I mean, I'm bringing my 0 out to like, you know, there to like 0.2. So I feel like something around there is probably what I want. I've gone back and forth on this for 2 days. 2 days, 2 weeks. But something around there.
I'm a little confused on how you're determining Q from this graph. Is it your deviation from the x-axis, kind of? You want it to be flat pretty much?
Q is how much the image position, the vertical image position, how much y2 depends on theta 1.
Okay.
Yeah. I want it to depend as little as possible on theta 1. If Q were 0, that would mean the y2 wouldn't depend at all on theta 1, and that's what we want. But we can't get it exactly equal to 0 everywhere over this range. Other questions? Now let's look at the lower right matrix element, because the lower right matrix element is our magnification. Y2 equals lower right matrix element times Y1. So look at that lower right matrix element. We get all of this. We set it equal to that. And then we plot it. And we find a range of magnifications from -1, -2 to almost, well, let's see here. In the range that we actually look at, we look from about -2 to -0.2 to +0.2. So let's narrow it a little bit so we can see it more clearly. From about -0.6 to -1.8. So we can change the image size by a factor of 3, from whatever it is out here, about -0.6, to whatever it is out here, 1.8. So if you can vary it by a factor of 3, that's reasonably useful. That's a good starting point. Any questions on that? Somebody must have a question. This process can't be that simple.
Professor, you said that we can alter the magnification by a factor of 3. You're basically saying that if we like let's say exceed over 3, like our quality would like decrease, or like what would happen?
I'm saying that once we go, I mean, you can make that, you could shift those lenses anything you want, but if you shift them by more than this, then all of a sudden you're going to start to notice a huge dependence on theta 1. You're going to suddenly notice the whole idea of a lens, right, is that the rays, if you're imaging from a point at a finite distance to an image at a finite distance, all the rays, no matter which angle they go at, they all arrive at the same point. So Y2 only depends on Y1. That's the idea of imaging, right? Do you understand what I'm saying there?
Yeah.
Okay. So it shouldn't depend on this angle at all, whether they go up or horizontal or down. Their arrival point over here shouldn't depend on angle. And that's true as long as Q is 0, or Q is so small that we don't notice it. But once we move the lenses by more than about 1/5 of a focal length, 0.2 left or right, once we move the lenses by more than that, then suddenly Q very rapidly increases. And if you want to quibble over it, we could argue, well, does it happen at 0.2? No, maybe it happens at 0.22. But once you get much past 0.2, then all of a sudden Q increases very rapidly. You could say, look, we're looking at this at a magnified scale. But you know, I could always demagnify it. And the fact remains that when I demagnify it, very quickly, it's rising. And it's even worse if I don't pick just the right lens spacing. Here, this is beautiful. If I go further out, then, well, now Q starts to become significantly different from 0. We can quibble over what we want it to be, but somewhere around here, it's just looking really, really flat. Does that clear it up, or you still have a question?
Yeah, that helps. That helps clear things up.
Anyone else? Then let's go into Zmax. So let's look at the Zmax file that I posted today. Triplet zoom, optically compensated. It's called optically compensated because it's the lenses themselves that make sure, it's the way the lenses work that keeps anything from, that keeps the image from moving. You know, so let's start by just looking at the 3D layout once you get it open. Maybe I should make larger Y displacements. Yeah. Okay. So object, lens, 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 image. And we'll worry in a little bit about this back extrapolation. Here's how I chose to implement it. There are many ways we could implement it. I designed this thing using the equations in the file. I determined that, okay, I set everything up so that our focal length would be 10, which means the focal length of our left positive lens would be 10. So this element power would be 1/10 or 0.1. And then this one would also be 0.1. And then this one would have a focal length of -5, so the element power would be -0.2. Then we could go back into Mathematica and we could ask a very simple question. All right, we've been designing so that the lens spacing would be about 0.6 focal lengths or 0.66. And for reasons, let's go to the middle configuration. I made that lens spacing 0.66 or 0.63 times 10. You could say 6.3. Why is it 6.3? Instead of 6.6? Well, first of all, I haven't fully optimized it. But second of all, the distance that we have to measure is the distance from a principal plane. And the principal planes are actually inside the lens. So we don't necessarily want to just make the spacing 6.6. The principal planes are inside the lenses. So Mathematica predicts that the lens spacing should be 6.6 something. When I optimized it for thick lenses, they're not that thick, but still they're somewhat thick. I get something pretty close. Then we could go into Mathematica and we could just say, okay, well, let's see here. S was 1 plus D over D, okay? So S is going to be 1 plus 0.66 divided by 0.66. That winds up being 2.5. And our 2.5 times the focal length. And our focal length is 10. So 25 point something. So I set it up like this. I've got 25, 25, 6.3, 6.3. Any questions on how I set that up before I start talking about all those extra layers that have 0 thickness if you're looking at configuration 2? And if you're looking at a different configuration, they're going to be something else. Anyone? Well, I decided that I would do the following. I decided that I would add this extra layer whose thickness could be 0. Or if you flip through the configurations, it could be 2. Or it could be -2. And then the next one, whatever this thickness is, it's the opposite. And then the next one is the opposite of that. And then the next one is the opposite of that. And I did the opposite with a pickup. I said, okay, take the thickness of surface 1 multiply it by -1. Et voila. There are other ways you could have done it. That's how I chose to do it here. We can talk about other ways later. Any questions? Anyone? So this is why, if you look on the right, you've got all these extra layers. Like over here, because it goes 25 to the right and then back -2. Here it just goes 25 to the right. Here it goes 25 to the right and then another 2. So that's why you've got these little extra features here, because I chose to do things in what wasn't necessarily the most elegant way, but it was relatively transparent to enter for these purposes. Here's the proof that it works. Spot diagram. Don't look at the off axis right now. You see how the on axis spots are all pretty much the same size. Of course, they're not perfectly focused. By now, you've been doing enough of these things to know that perfect focusing never happens. But you see how they're all roughly as bad as each other. You know, this one's not perfect. This one's pretty much the same. This one's slightly worse, but they're pretty close. That means we have a good zoom lens. Any questions? Somebody must have a question.
Our configuration 2 is like our symmetric case where there's no change. Okay.
Yep.
Now, is that the best spot size out of the two, or should it be?
It's what we designed for, so yeah, it should be pretty close. We can always see what happens if we open up the aperture. Can't open it too much. If I go to 3D layout, yeah, it doesn't hit the edges too much. It hits the edges kind of there, but still, if we go to there. Now, one thing that's nice is because I don't do any pickups, I can do some optimization. So I could, pickups complicate optimization. I could do a quick adjust there. And then I could look at our configuration matrix spot diagram. And it gets a little bit better. You know, nothing's perfect, but still. They're again comparable. You know, we defocused and we widened the aperture, and of course our aberrations get worse in all three cases, but they get roughly similarly worse. So in some sense, it's behaving like a zoom lens, a very amateur zoom lens, but still a very real zoom lens.
And those spot diagrams are from the same exact image planes, right? It's not from your 2 millimeters greater or 2 millimeters closer, right? Or is it?
I need to know exactly what you mean by that, because in this case, the distance here, the distance is 25. In the middle case, it's 25. Here, the distance is 23. Here, the distance is 27, and it should be, because in one of these cases you moved, or no, here it's, yeah, here it's 27. So when we move the lenses, you know, we should get different spaces. The whole idea is that, yeah, we do shorten the last distance or increase the last distance depending on how we move the lenses. When we move the lenses, the distance from the last lens to the focal plane, sorry, to the image plane, the distance from the last lens to the image plane definitely changes. but the image plane itself doesn't change. It's because of the way these things all got drawn so that these three lenses are all in the same place. If I had spent a little more time on thinking about how to set this up, then I could take this lens here and shift it to the right, and this plane would line up with this plane. And I could take this lens here and shift it to the left, and this plane would line up with this plane.
Okay.
All right, let's take a 10-minute break, and then we're going to go over the hardest lens I've ever worked with. Well, the hardest lens I've ever simulated.
I feel like today's a tough day for some reason.
I have spent a month working on this, believe it or not. This is the single most difficult thing I have ever done for this class.
Yeah, I might have to watch this lecture again and come back with more questions.
Okay, that's fine. I also have to watch it. No, zoom lenses are hard. All right, that's just how it is. Zoom lenses are difficult. And I'm still working on the zoom lens assignment. I wasn't going to write the zoom lens assignment until after today because I wanted to see how things go. I just thought to myself, oh, you know, how bad could zoom lenses be? I mean, you know, we see a lot of them. It'll be fun. Let's figure out how they work. And yeah, I'm gonna have to come up with a very, very gentle zoom lens assignment for you guys.
Well, thank you for understanding that it's hard.
Hey, you have no idea how many days I've spent trying to get the Mathematica matrix calculations to work. And then trying to get it into Zmax. These zoom lens designs are the most finicky thing that I've ever worked on for this class. And I've been teaching this class for 11 years, and zoom lens designs are the most finicky thing I've ever worked on.
Is this your first time like adding zoom lenses to?
Yeah.
Okay.
I said this fall, I can never, if I were to just, there are some professors whose lecture notes were written down in the 1970s and haven't been edited since.
Mm-hmm. Yes.
And I can't bring myself to do that.
Yes,
Every year I'm like, hey, let's add this thing. Hey, let's add that thing. Hey, I just read this interesting article. I should talk about that. Hey, I just went to this optical society meeting. I should talk about that. Then once I'm in the middle of the semester and I got a bunch of other things to do, oh crap, this is hard. Why did I decide to add this during the week that I have this committee thing and this department meeting, and then I got this thing in my other class, and yeah.
Well, thank you for working hard for us.
Well, no, it's, look, actually, that's the fun part. That's the fun part. It's like, if I have a choice between saying, do I want to spend a few weeks really trying to understand the lens, or do I want to spend a few weeks doing some silly thing that the administration wants from me? Which one do you think I'm going to choose?
The lenses.
Of course.
Yeah, you told me one time that you were teaching like all introductory physics courses, and you're like, just come to me with Zmax questions, please. I need something better to talk about. So it's always fun to work on these problems rather than others.
Yeah. All right. I gotta do something during the break. Save what modifications we've made. And output. Save. Quit. Okay. Let's get started again. So that lens that we just worked on was a lens for an object at a finite conjugate, finite distance. But I was looking at a famous lens design book by Rudolph Kingslake, a lens designer whom some of my friends from Rochester speak quite highly of. And what Kingslake did was he talked about a lens for objects at infinity. And it still works off of the same basic idea, except that he if you really there's to really get at like the principle behind these lenses, you have to think about virtual objects. If you really want to do things with the thin lens equation to try to understand where the image is formed by each lens, you have to recognize that in this first case, we've got basically a virtual object there. Instead of a virtual image, we have a virtual object. The rays look like they're going to a distant point. So this is a virtual object. And as you move it back and forth, that shifts this the image formed by this one, which then serves as a virtual object for this one. And all of these back and forth shifts wind up essentially canceling. And when I look through Kingslake's book, he did it in a rather confusing notation. But, basically we're going to have F1, D12, F2, D23, and F3, and S. And you follow the same procedure. 1, find S. 2, we move these lenses. Move 2 of the lenses. We shift this one by a distance X, and we shift this one by a distance X. And when we do that, now this distance is D12 minus X. And this distance is D12 plus X. And this distance is S minus X. So we shift the lenses. And really, if we wanted to figure out where the image actually forms, there's an additional delta S.
Shouldn't the middle D12 be D23?
Oh, yes, thank you. D23 plus X. Let me try to make that at least sort of vaguely readable. D23 plus X. So we shift the lenses. And then we see what happens. And I spent a very long time working on this, because what you're supposed to get is you're supposed to get the delta S versus X looks something like this. By the way, it looks cubic here because we've got 1, 2, 3 X's in there. X shows up in 3 matrices. So we multiply by S 3 times, we get a cubic polynomial. Up here, we were getting, even though I drew it, I sketched it to show the idea, we actually got things that looked more like that. And the reason why is that X shows up 1, 2, 3, 4 times. And if X shows up 4 times, then when we multiply our matrices together, we're going to get a quartic polynomial, right? And so I kept thinking that I should get a polynomial that looks like this, but I wasn't. I was getting much uglier things. I was getting things that were still cubic, but they would tend to look like, oh, that's not good. They would tend to look like that, all right? And I'm going to show you why they looked like that by sharing my other screen and just highlighting something from the book. It gives all these focal lengths to many digits. All right. He says that the focal length of the front lens is 7.15959. And the focal length of the middle lens is minus 1.95959. And I've got to be honest, I've tended to be a bit lazy. I would be like, okay, 1.96, 3.35, 7.16. What could go wrong, right? That is what went wrong. What went wrong was me just saying, 7.16, why not? 1.96, why not? Shouldn't be that sensitive. Well, it is. And the reason why basically is that polynomials, what does a polynomial do? If you just draw some random polynomial, it's going to probably wiggle. Wiggling is what polynomials do. To get a polynomial to flatten out is actually kind of difficult. The polynomials that and here I'm giving you the theorist's explanation. The engineer's explanation would just be like, look, you have to make it precise or it doesn't work. Theorist's explanation is if you just pick some random polynomial, it's going to wiggle. The polynomials that don't wiggle are special, all right? You've got basically a bunch of very closely spaced roots, and you've got a very small amplitude of the wiggle between them. Well, if you want to get special polynomials, you got to be very precise in specifying them. And I wasn't precise in specifying them. So open up the one that says Kingslake R notation. I'm doing it in R notation because he originally specified the spacings in a very different way. Again, we define the commands, we define the triplet. I chose to make F1 1, but I don't think I'm going to do that here. You know what? Let's do it the way that he did it, except we're not going to say 7.16. That would not be good. We're going to do 7.15959. All right. We're going to define F1 to be 7.15959. And then we're going to actually just define all of those things right here, right now. So F1 is that, and F2, no, we'll leave them all alone. We'll leave them all alone. Now that I think about it, we should just leave them all alone. And we'll go through the steps. So I'll show you what I mean here. So now we're focusing an object from infinity. So now we want the lower right matrix element to be 0 because we want y2 to only depend on theta 1. We want y2 to only depend on what angle the rays were coming in at when they hit the lens, not whether they hit the top or the bottom of the lens. We want all of the rays to come to the same point. Whether they hit the top, the middle, the bottom, whatever, they should all come to the same point there. So the lower right matrix element should be 0. So we solve for S, and we get this answer. We paste it in, and we get that. And we say, all right, S equals that. And then we simplified something that's ugly, ignore it. Then we shift everything, okay? Then we say, well, now we're going to have a triplet with, again, F1, F2, F3. We shift everything. Then we solve for the image shift. And we get something god-awful ugly. We can just copy the whole thing. Make sure you don't copy the curly brackets. That's very important. It looks god-awful ugly. Let's plot it. And I originally had the left lens F1 equal 1, and then I had to rescale everything to that, but take out all those divided by 7.16. Let's just actually use the numbers from that book. Then oh God, this is, what was I thinking here? And by the way, I was being lazy. It should not be 1.96. It should be negative 1.96. You know what, I'm sorry, whenever I decide to be clever and change something on the fly, this is what happens. Let's change all of that. Let's just plug in values for F2 and F3. Let's just plug in F2 is negative 1.95959. Let's just plug in F3 is 3.35410. Let's just plug in D12 equals, Christ, what was it? I deleted it. This is what happens when I try to be cute. What was it in there? It was something, some number divided by 7.16.
Was it? I just remember one other number, 0.95959. Like it happened similar to the first one.
FA plus FB minus X. So it's going to be FA plus FB plus FB minus X. Don't worry about what these minus X's, what these X's are. Kingslake used a really weird notation. I'll do it this way. It's going to be $7.159. Sorry, 7.1. No, 5959 plus or minus 1.95959 minus 2.2, and D23 be the second plus the third, so it'll be negative 1.95959 plus 3.35410 plus 0.3 Let's just see what that plot looks like. Okay. It looks like very little because I considered too narrow of a range. So we go to minus 0.5 to 2.5. That is basically the polynomial from the book. I can show you that he said that you would get, he does his curve sideways, but basically this is the same cubic polynomial that you get in the book, just rotated sideways. All right, now we are going to copy this. And then let's try changing some of these numbers. Let's just try changing this to minus 1.96. Well, that doesn't matter much, but we'll just truncate these things one at a time. Oh, great, now it works. I have never been so embarrassed to have something work. I spent a month trying to get this work, and I finally had to include all the decimal places before it would work. Then after telling you guys no matter what I did, it wouldn't work. Then I finally put it in with all of the decimal places. without all of the decimal places, and it works great. Okay. Oh, crap. It's a more robust thing than I thought, because this thing was not working. Normally I go to class and something doesn't work and I say, I swear to you guys, when I tested all of this before class, it worked. And now I'm telling you that when I tested all of this before class, I needed all of the decimal places or it wouldn't work. And lo and behold, I take out some of the decimal places and round, and it works fine. And I've never been so embarrassed to have a good result in my life. But what I want you to take away from this, besides the fact that Zoom lens design is so hard that your professor spent a month on it, failed to have it work, and only now does it start to work and it won't stop working. What I want you to take away besides that is the idea that we've got a very tiny image shift. These numbers are in centimeters. And so the image shift is less than a millimeter. All right, if our final image distance is, well, let's just see what our final image distance would be. Our final image distance would be this. So I copy it, I paste it, 1.69 centimeters. And the image will shift by less than a millimeter. That's pretty good, right? This is a good lens design. Any questions so far? I think I hear hail hitting the roof. Somebody must have a question. Well, one question we could ask is, what is the magnification, all right? Or what is the effective focal length now, right? So we could ask what that is, and I hit Shift Enter on the wrong thing. You could just ask, what is that lower left matrix element? It's the focal length when you have an object at infinity. And then we could put in all of that. Just copy that entire thing and paste it in and say that is our focal length. And now let's manipulate it. And now I will just not divide by the 7.16. And I'll just say that our range is going to be from minus 2.5 to minus 1.5, something right in the middle of that. And I'll just not divide by the 7.16. And all right, if F3 is 3, I'll make it changeable between 1 and 5. Why not? And if this is 3, I will make it adjustable between 1 and 5. And if that is 1.69, I will make it adjustable between 1 and 3. And then we can see what our range of focal lengths will be. We get a focal length of 10 point something for x equals 0. It goes down to 8 point something. This F3 is the thing that the focal length is most sensitive to. If we compare with what's in the book, we can get focal length of anywhere between Well, clearly I did something wrong. I feel better now because earlier everything was working and I couldn't explain it. We can get a focal length that's anywhere between 10 point something and 3 point something. So about a factor of 3 change. I want to show you one more thing and then we're just going to probably end a few minutes early. And your ZMAX assignment for zoom lenses, which I will post sometime this weekend, will be to implement some of this in ZMAX and just see how robust it is in practice. That was a lens with three, it was a system with 3 lenses. So X shows up in 3 places, we get a cubic polynomial. Now go to Kingsley Quartet, because he also did something with 4 lenses. And with 4 lenses, that's the one where if you're not super, super careful, you don't get things to work. So this one actually has 5 lenses. There's 4 lenses that do the zooming, but they produce a virtual image. And the 5th lens takes the virtual image and turns it into a real image. And so we define a quartet. It's got 4 focal lengths and 3 lens spacings and an object distance. And we're just going to work with the 4 lenses because we just want to figure out where the virtual image is. Once we've got the virtual image somewhere, then we can always add a 5th lens. But the hard part is to get these 4 lenses to work. And the idea is that we shift the 2nd and 4th lenses. So we define this quartet. And we're just going to see what the image shift is. And then we're going to plot it. And if you use rounded numbers, you get this. But if you use numbers that aren't rounded, you get this. So what we're looking at on the vertical scale is how much the image is shifted for different displacements of the 2nd and 4th lenses. We move the 2nd and 4th lenses back and forth by a distance x, and the image gets shifted by this much. Well, then we use more precise numbers. And when we use more precise numbers, we get this. We get that the image barely shifts at all. And so the lesson I want you to take away, and I will try to write this up more accurate, more transparently. The lesson I want you to take away is that these are finicky designs, okay? Because we've got a 4th order polynomial. 4th order polynomials wiggle a lot. The higher the order of the polynomial, the more it wiggles. In order to get a polynomial to be really, really flat in one part, rather than just wiggling, you need to have very carefully chosen numbers. And I initially did not have carefully chosen numbers. I used rounded numbers. And then down here, I used numbers to all of the decimal places that he gives in the textbook. You look at the section on 4 lenses, and you look at the numbers that he gives. See? Any questions? So here's what I want you to take away, besides the fact that these are so hard that after 4 weeks, I still only have so much to say. I want you to take away that the idea is to come up with a combo of lenses where you move 2 of them, you keep the rest of the lenses and your detector fixed, and the image barely shifts. And in all of these graphs I've been showing you, I'm saying this one's bad because the image shifts a lot as we move the lenses back and forth. This one's good because the displacement of the image hovers around 0 as I move the lenses back and forth. This one's good because when we look at the configuration editor, we see, sorry, the multi-configuration spot diagram, we see that when we move the lenses back and forth, the spot size barely changes. That's what I want you to take away, that the whole goal here is to find a design where if you move the lenses, the position of the image barely changes and the quality of the image barely changes, at least for some range of movements. Somebody must have a question.
And the most like optimized way to do this by basically by changing the magnification without moving the image plane that much is by these 2 lenses that you showed us today.
The more lenses you put in there, the better. Because the more lenses you put in there, at least in principle, you have a higher degree, well, actually, there's a few things. First of all, you have a higher degree polynomial, which means that there are more coefficients to play with. So you can't really do anything to the shape of a parabola. A parabola just is what it is. But a cubic has these multiple wiggles that you can play with and adjust. Parabola is what it is. A cubic or a quartic, there's a few different wiggles. And if you can get those wiggles to all just line up right and cancel each other out, conceptually, it's almost a little bit like wave interference, except that the mechanism is very different. But the idea of kind of adding up some wiggles so that they all cancel out and everything just kind of remains flat, it's kind of like that. It's kind of like destructive interference of light.
And the nice thing about these 2 lens systems is because the mechanism is easy because you're just moving 2 lenses rather than if you were to move all 3 of them or something like that. So it's more practical.
I mean, somebody could have potentially moved 3 out of 5. I'm sure somebody's done a 5 lens system where they moved 3. There's probably someone somewhere who's done a 6 lens system where they move 3 or whatever. But in general, you don't want to move too many things.
Okay.
All right, if there are no other questions, then class is done. Starting next week, we're going to do wave optics, and we're going to build up towards understanding the resolution of a lens, and then we'll do some stuff with modeling thin films for the rest of the semester. Have a good weekend.
Thank you for struggling with this for a month.
I will be compassionate when I write the Zoom lens assignment.
All right, perfect. Thank you.
Maximum, Julian, you have questions? All right, Julian, if you don't have a question, then I'm going to close the class session.